Welcome to this explainer. Today, we're diving into a technology that is literally reshaping our world. We hear the term constantly, but I want to kick things off by posing a very fundamental question. What is it that makes a machine truly intelligent?
Think about the gadgets we use every day. A calculator, for instance, is incredibly fast, right? But it only does exactly what you tell it to do. It's just a tool. But what happens when a machine crosses that line from simply following rigid instructions to actually being able to think, adapt, and learn? That transition from a rigid tool to a thinking machine is exactly what we're unpacking today.
Okay, let's dive right in. At its core, artificial intelligence is a machine that actually mimics human traits. It doesn't just execute code blindly. It can collect data, understand it, analyze it, and then make autonomous decisions to solve real-world problems. And the absolute most important part? It improves on its own from past experiences. It learns, it predicts, and crucially, it decides.
Section 1. The 3 domains of AI. To really get how this works, you can think of AI like a braid made up of 3 interacting strands.
The first strand in our braid is data. In the domain of data for AI, machines learn from historical statistics and past patterns. By ingesting massive data sets, the AI begins to recognize trends, which allows it to predict future outcomes based entirely on what has happened before.
A great example is an AI trained to play rock, paper, scissors. It's not just making random guesses. As you play against it, the AI is constantly collecting data on your previous moves. It learns your patterns, predicts what you're going to throw next, and adjusts its own move to beat you. It's literally using your own historical data against you in real time.
The second domain is natural language processing, or NLP for short. This is the strand that deals with communication. NLP enables machines to comprehend, interpret, and process the words we speak and write, allowing computers to extract meaning from human language, just like a regular conversation. You can see this NLP magic in action with games like Semantris. It's a word association game where you provide a textual clue, and the AI instantly analyzes all the other words currently in play. It then ranks and chooses the words it thinks are most semantically related to your clue. It's attempting to understand the hidden nuances and connections between human concepts on the fly. And then we have our third pillar, computer vision. If NLP is how a machine reads and hears, computer vision is how it sees. This domain allows machines to process, analyze, and interpret the visual world, identifying objects in images and videos much like our own eyes and brains do.
Google's Quick Draw is a brilliant way to experience this firsthand. You get a prompt to doodle something, let's say a butterfly. And as you draw, an AI neural network watches your strokes in real time. It analyzes the visual data as it unfolds and tries to guess what you're drawing before you even finish the sketch.
Section 2, AI in the real world. Let's look beyond the games to see how these exact same concepts power the tech we rely on every single day.
Just think about it for a second. Your smartphone's face lock? That's computer vision detecting and matching your facial features. Voice assistants like Siri or Alexa? That is natural language processing, figuring out the meaning behind your speech patterns. Massive banking systems use data AI to analyze customer profiles to predict loan defaults. And over in healthcare, computer vision is converting 2D medical scans into interactive 3D models to help doctors. The fun games and the incredibly serious tech share the exact same DNA.
Section 3, the AI project cycle, specifically problem scoping. So how do we actually take these complex concepts and build a functioning, real-world system? Well, the answer is structured methodology. Before writing a single line of code, we use a framework called the 4Ws problem canvas. We ask who, what, where, and why. Who are the stakeholders? What is the actual problem and what's the evidence for it? Where exactly does this occur? And why will solving this actually benefit people?
Section 4. Case study. The cotton ASAP. Let's apply this framework to a really high-stakes issue, agricultural pests.
If we use our problem statement template to map out this scenario, the pieces come together perfectly. Who? The farmers. What? Their cotton crops are being infected by a pest called the pink bollworm. Where? On the crops in their fields. Why? Well, an ideal AI solution would benefit them by figuring out the exact amount of pesticide needed, knowing the right time to spray, and ultimately increasing their crop production and profit.
And this exact scoping exercise led directly to a real app called Cotton Ace. A farmer sets a physical trap, snaps a picture of the captured pests with their phone, and uploads it. The app then uses computer vision to detect the insect and gauge the infestation level. Then, based on rules laid out by entomologists, it recommends the precise pesticide treatment needed. It totally takes the guesswork out of farming and uses computer vision to literally save livelihoods.
Section 5. Fueling AI with data. Because honestly, even a brilliant app like CottonAce is completely useless without the right fuel, which is data acquisition.
Now you have to understand the difference between two crucial types of data here. First, there's training data. This is the historical information you feed into the machine so it can actually learn the patterns. Second, you have testing data. This is a separate, entirely new set of information used later to verify if the machine actually learned correctly. If your training data is flawed from the start, your testing data will quickly reveal that the AI's predictions are entirely useless.
Because the whole system hinges on this data, we have to stick to some strict best practices for acquiring it. The data must be authentic and highly relevant to the specific problem you scoped out. And perhaps most importantly, it absolutely must be ethically sourced. Extracting private data without permission is a complete non-starter. We have to rely on ethical, open-source information to build these systems the right way.
Once you've got that solid ethical data, you need to understand how the different pieces interact. By drawing system maps, we can visualize the complex feedback loops, like how the amount of pesticide used today affects the soil tomorrow, so we can architect a responsible solution that actually achieves our goal.
Section 6. The generative AI future. As we look beyond the basics, we are entering a rapidly evolving frontier.
By utilizing incredibly deep neural networks, generative AI is pushing the boundaries of what machines can do. It's not just analyzing old data anymore, it's synthesizing brand new text, generating photorealistic images, and creating dynamic, original content entirely from scratch. It's the culmination of years of massive innovation in the AI space.
So we've seen how this all works. From an AI playing rock, paper, scissors to saving a cotton farm, right up to the cutting edge of generative AI. We've explored the 4Ws framework and the absolute necessity of ethical data. So the only question left for you is this. Armed with these tools and this understanding, what real-world problem are you going to scope, and how will you use AI to make a positive impact?